Welcome to this video on initial rates experiments. So two aims from this video: that we'd know what an initial rate is and that we'd know how to measure initial rates experimentally. Now an initial rate initial just means start. Okay, so remember the definition of the rate of reaction either with respect to a reactant or with respect to a product was simply the rate of the reaction is the change in the concentration of reactant divided by the change in time. We needed a negative sign there. Here, if it's a product, then it's the change in the concentration of product divided by the change in time. And this minus sign here just to make it positive. Now, if we want to do the initial rate, remember any rate is just a slope at a particular time on the graph, so we could measure the rate at that point, or that point. Now the initial rate is going to be the slope at the beginning, so it's going to look like that. So these are tangents just drawn right at the beginning, and if we calculate the initial rate using the reactant formula, then initial rate, I'm going to give it a little subscript 0. Rate 0 is the change in concentration, so it's gone down by -1. Change in time is about 20 seconds, got to put a minus sign in front of that, so 0.05. And remember it's concentration per second, so mole per decimeter cubed per second. And we can do exactly the same thing here, and you should be able to satisfy yourself that you get exactly the same rate whether you use the product or the reactant. Now, so the first way that we can get initial rates data from experiments is just to do one of these continuous monitoring experiments that you've been used to doing as shown in previous videos, and simply take the trace that we get, draw a tangent at time 0 and calculate the gradient, which will give us the initial rate. Now that's actually quite a time-consuming process. You'd effectively have to do several experiments at different conditions and then get these traces, measure these gradients, so it's a bit tedious. So a faster way is using something called a clock reaction. A basic idea here is, let's say we have a reaction here, and click the link to watch a video which is actually showing you a real example of this. But let's say at time 0 we've mixed our reagents and we've got a colourless solution. Now imagine if this is a precipitate that forms that starts to make the solution a bit cloudy, and eventually our smiley face that's behind our solution gets completely obscured, and that happens at a time tau, Greek letter tau. So what we can actually do is use this time that it's taken for this to happen to give us an idea of how fast the reaction is. And you can probably see that the faster this takes, the quicker this takes, so the shorter tau is, the faster the reaction is going to be. So that's one example of precipitate forming. Another one could be a very rapid color change, so it might take time tau to go from colorless and then suddenly this color appears. Again, click the link to watch a real example of a reaction like that. Typical one's called an iodine clock. Or it might be the reverse, where you've got a general fading. You could have a very sharp fade, the sort of reverse of this reaction, or you could have a general fade. So an example of this would be the iodine propanone reaction. Again, click the link to see suitable video, but same idea. Time 0, after a while there's no color left, time tau. Okay, how do we actually get the initial rate from a clock reaction? Well, imagine we've got the product forming over time, and then this concentration here is where the product is visible. So we get a color change at this red line, this threshold or critical concentration. So imagine that at a concentration of 0.2 moles per decimeter cubed, something happens. Let's just zoom in on that area. We'll just go here. So imagine, so this is a visible product. Now, what would the rate of reaction be? So remember, initial rate is change in concentration of product divided by change in time. So what we can do is get the average rate up to this point. I'll just switch color just so that you can see this a bit more easily. So you can find the average rate between this point and the start. So what's the change in concentration during that time? Well, change in concentration of product has just gone from 0 to 0.2, so it's changed to 0.2. And the change in time, that's a hopeless line, If we draw it down like this, it's around about 4.5 seconds. 4.5. So if we work out what that is, then we've got a rate of around about 0.044, and I'll leave the units off. So that's the rate that we've actually managed to work out from this. But what I want you to see is how have we actually calculated the rate? Well, what we've done here is we've done the change in concentration divided by, this is just our value of tau, so this time here is our time tau. And so what you can see here is what we've done is concentration or critical concentration divided by tau. Now, in a typical clock reaction, we don't know what this critical concentration actually is. But in actual fact, it doesn't matter, because as long as this is the same every time, so this critical concentration of product crit, and this is the same all the time, because it always, you only need that much product to become visible. And so if all we're going to be doing is comparing initial rates under different conditions, it actually doesn't matter what this is. So we can say that the initial rate of reaction for a clock reaction is directly proportional to 1 over tau. And so actually we can just use 1 over tau as an approximation to the initial rate in these experiments. So that is the key result for a clock reaction. Now, one question that arises from this is, how accurate is this? And you might want to pause the video now and just think about what has to change, what could change here to make this more or less accurate. Okay, let's think about it together. So, at the moment, this purple line here is showing you the actual tangent at t equals 0. And the rate, initial rate, is actually 0.05 moles per decimeter cube per second. This blue dotted line here is the average rate calculated using a critical value here at a concentration of 0.2. So this here is the initial rate approximation if concentration of the product, the critical concentration, is 0.2 moles per decimeter cubed. And it turns out that that is 0.044 moles per decimeter cubed per second. So there's around about an 11% error. So why is that error? Well, it's because we're assuming that where this graph is actually starting off very steep here and curving, we're assuming that actually the rate is constant over that whole length of time. So how do you actually get the reaction to be more accurate? Well, what you need to do is have a situation where your critical concentration is actually smaller, so that you're actually assuming an average rate is true for a time when the graph is actually approximately linear. So the smaller this critical concentration, the better your approximation should be. So a couple more graphs just to show this. So if we look at this case, you can actually see the blue line. So there is a blue line lurking here. This is if the critical concentration is 0.1. You can see here that I have actually drawn a dotted blue line, but it overlaps completely. So here there's no error. The initial slope and the approximate initial slope are spot on. In contrast, if I work with a situation here where I'm looking at critical concentration of 0.4, so before I see anything, I have to have had 0.4 mole per decimeter cube product in the solution, then in that case, the approximate slope here, the blue one, is well off what the true initial slope actually is. So here you get a much bigger error. So, in summary, initial rate's really powerful experiment. Subsequent videos will show why. You can find the initial rate by drawing the tangent to a concentration time graph at t equals 0, like this. Or you can find the initial rate by using a clock reaction, if your reaction happens to be able to be set up like that. And you can find it as 1 over tau, where tau is the time it takes for some kind of specific amount of product to form. And it must be the same amount of product that forms in every investigation, otherwise you really are going to have a mess. So tau is the time it takes, and these are accurate provided it's around about less than 15% of the reaction that's taken place.